Hello everyone and welcome back to another video. This is a square, but recently I saw this post floating around saying that this was also a square. While I get what the post was trying to do, after all the shape does have 4 sides of equal length and 4 right angle corners, I don't think this counts as a square because of the 2 sides that are curved. This idea did get me thinking though, and pretty soon I came up with this. Behold, a new type of square. The cylinder this square is on has a length of 1 and a radius of 1 over pi, which means it has a circumference of 2 and a half circumference of 1. This means it has 4 straight sides of equal length and 4 right angle corners, which makes it a square. Some of you might be confused because I called the lines on this cylinder straight even though they appear to be curved. The reason that these lines are straight is because that they are non-Euclidean two-dimensional lines on a three-dimensional surface, instead of being three-dimensional lines. The best way to visualize this is to imagine a circle living on the cylinder. It can choose to move forward or to turn in some direction. If the circle moves in a straight direction without turning, the line it leaves behind is straight, even if the surface that it is on is curved. After creating this new type of square, I noticed something. That being, if you follow the square's perimeter in one direction, the line sometimes turns left and sometimes turns right. This differs from a standard square, which will either always turn right or always turn left depending on the direction that you follow the perimeter. This got me questioning if there were possibly other squares that could be made. After all, with 4 corners and 2 possible states for each corner, it would seem there might be 16 types of squares. Looking into it further, the 16 possible corner combinations can actually be simplified down to 4 types, as 2 are the standard square, 1 going each way around the perimeter, 4 are a cylindrical square that I showed before, just starting the sequence at a different corner, 2 are a pattern of alternating left and right turns, and lastly, 8 of them have 3 turns in one direction and 1 turn in the other. Before I continue, I should probably name these squares to avoid confusion. For simplicity, I decided to name them based off a repeating pattern on a two-dimensional plane. The standard square doesn't need to be extended at all and looks like, well, a square, so I just decided to call it the standard square. The cylindrical square looks like a square wave, so I decided to call it a wave square. The alternating sequence looks like a staircase, so I decided to call it a stair square. Lastly, the 1 and 3 sequence only repeats twice and looks like an infinity symbol, so I decided to call it an infinite square. While these infinite patterns look pretty, none but the standard square and a wave square on a cylinder satisfies being a 4 straight equal length-sided polygon with 4 right angles. So the next step was to find the surfaces for the stair square and infinite square so that they could be brought into reality. While I figured out the necessary surface for the infinite square first, due to its simplicity, I ended up modeling the stair square first. As you can see, each of the square's corners are right angles, and each of the sides go across one side of the surface and around one of the surface's beveled edges, giving each side an equal length. Fun fact about this square/surface, it looks like an AirPod case. Yes, I know, plenty of people have told me this. Personally, while I can see the resemblance in the material that I made for this model, putting them side by side, they really aren't the same. Lastly, we have the infinite square, which looks like the stair square with a massive tumor on it. This is because we want 3 of the corners to be on the top face of a surface and 1 to be on the bottom face of a surface. Since there are 2 edges that wrap around the beveled part of the surface, they would normally have larger side lengths than the other 2 edges. However, thanks to the protrusion, we can extend the other 2 side lengths to match in size. With that, I have shown off possible surfaces to generate all 4 types of squares. However, I'm sure that some people will argue that because these squares don't follow some of the rules that standard squares follow, that these should not be considered squares. The first of the 2 big rules that these new squares don't follow is that they don't have an area that is equal to their side length squared. I would argue that while this is a rule for Euclidean squares, I don't think this is a rule for non-Euclidean squares, since with a surface like this, while the shape is clearly a standard square, its area is significantly larger than its side length squared. The second of the 2 big rules that these new squares don't follow is that all squares are parallelograms. I would actually argue that the wave square is a parallelogram, as the lines traveling down the length of the cylinder are clearly parallel, and the lines going around the circumference are also parallel, as any line perpendicular to one of the lines will be perpendicular to the other line. I feel like a similar argument could also be made for the stair square, as if you extend all the lines infinitely to create 4 loops, it looks like the loops can be paired in parallel sets. Sadly, the infinite square is not as kind, as when looking at the protrusion, a perpendicular line will just loop around the protrusion and never intersect with the edge is supposed to be parallel to. I would personally say that again, this doesn't really matter for non-Euclidean squares, since just like with the area, a standard square can also break the same rule if on a surface like this. So with that, I am happy to announce these 3 types of squares to the world. Well, that's what I'd like to say, but while these polygons do have 4 right angles, if we instead ask how many interior 90-degree angles they have, none of them have 4. Instead, all of these polygons have some interior 270-degree angles, which invalidates them from being squares. This, however, begs the question, if these polygons are not squares, what are they? They do follow some rules, so I feel like these polygons should have some classification, but as far as I know, there is no pre-existing way to classify them. So I personally started calling them ticked polygons. With that being said, my current definition of a ticked polygon is that an n-sided ticked polygon will have n straight sides of equal length and n interior angles, each with a value of -m times 360 degrees divided by n, all plus 180 degrees, where m is any integer. Under this new classification, we could call individual ticked polygons the same as their regular polygon counterpart with a prefix based on their values of m. While doing so, it would probably make sense to say that a ticked polygon's name is the first name that would appear in a sort of all the ticked polygon's duplicates. For instance, a standard square would be a 1, 1, 1, 1 square. A wave square would be a 1, 1, 3, 3 square. A stair square would be a 1, 3, 1, 3 square. And lastly, an infinite square would be a 1, 1, 1, 3 square. I guess with this naming structure, I did invent 3 new types of square with this video. Just not the regular polygon type, but my own new type of polygon. All that being said, at the end of the day, I am no mathematician, just a guy who likes thinking about non-Euclidean geometry and higher dimensional spaces. So if there already is classification or research on geometry like this, I would love to hear about it in the comments down below. Personally, I enjoyed making these models, so I might make a follow-up about this sort of geometry in the future. Let me know if that would be something you would be interested in by liking the video or leaving a comment. With that being said though, thank you all so much for watching, and I will see you guys next time. Goodbye!